So this is the modelling that I've been doing, and so this was done with the purpose of trying to explain the data that was extracted from. So the blue section at the top.
Yeah, he did some modeling of it and stuff like that just to demonstrate that if you track the center of mass of that slinky, that center of mass of that slinky is accelerating down with gravity, right? And so the whole point, I mean, this podcast I was listening to was not specifically just like, let's talk about slinkies. It was just talking about how stuff like this happens in life all the time, right? Where there's things set in motion that you cannot change, and that eventually it's just going to slam into you. And then they give some examples. One example of well, there are a couple of examples. One example of like something in motion that takes forever for it to hit us. Like, if, for instance, if the sun disappeared right now, just like disappeared, like what would happen? Nothing, right? Nothing would happen for 8 minutes, right? And then in 8 minutes, then all shit would break loose, right? Like we would fly off on a tangent, right? Because it would take 8 minutes for the gravitational waves to stop coming here, right? So it would take 8 minutes before that hit us, and then we would fly off on a tangent, right? If you believe these things, right? You fly off on a tangent, right? Everything would go dark 8 minutes later, and so it happens, and then there's nothing you could do to change it, and then 8 minutes later it would hit us. And so they use that as an example. The other thing, another place where this gets used is in ballistics, right? So they actually have we'll watch this here. Long rod penetrating ammunition here. Okay, ammunition. Okay, so this is cutting edge graphics here, but they do this if you're going to shoot. And we'll talk about, there's some of these dynamics principles that really. There's way more people on this side. See, maybe people will start migrating over to this side so that I lecture them. But military and weapons are actually a really cool way of demonstrating a lot of our dynamics concepts. So this is actually one of the places where it's a perfect example. The other thing I should mention too, an old joke about this is the difference between a mechanical engineer and a civil engineer. Mechanical engineers design weapons. Civil engineers design targets. So you may have heard this before. Okay, so I think that's a pretty good description between the two. But anyways, here are some mechanical engineers. They take advantage of this idea of wave propagation and how things are in motion. So this is what they have certain ballistics that they shoot at, like tanks, for instance. And they're long rods that they shoot at them, and it's the same concept that we saw before with that slinky. The first part of the rod hits it, but it's going so fast that it can't tell the back end to stop, and so the back end just keeps plowing in, and then it just eventually will penetrate through the thing they're shooting at, right? And then they get a little advanced. It's like, oh, if we shoot rods like this, you need to stabilize them, so let's put a little tail on it. Let's put a little point on the front of it, right? Let's shoot it out of stuff. This cutting edge. So that thing right there, does anybody know what that's called? A sabot is what that's called. And so, see, mechanical engineers do cool shit, right? Like, what's the best way? That's a sabot, and so that's something that's there to kind of catch whatever the pressure is behind that shoots it out of there and get it spinning the right way and stuff. But then you don't want that sabot traveling with it, so it sheds the sabot as it's going. You can see the rifling in the barrel that gets everything spinning inside there. So building it comes out, right? And then it ejects its sabot. And that's cool stuff. So this is projectile. This is now just a projectile. Here's some examples of it, right? I believe that's concrete that this projectile is passing through. They have something where it's showing it going through steel plates. Going through a car. All right, let me show you. I got a couple others related to this. These are cool. Where it's like a slow motion of one of these things shot. You can see the sabot gets ejected from it. The sucker travels along it. It's cool that they can even take a video of this, right? a projectile fly. I mean, it's like it's literally taking a picture of a bullet as it flies through the air. Right? Actually, one of the videos I ran across yesterday actually shows how they do it. They just have a stationary camera, and it's shooting at a mirror, and the mirror rotates, and so that's how it's able to track it as it goes along. I thought they showed one where it shows it just slamming into stuff. Maybe I didn't stay on this one long enough. I thought I had a really cool one that showed it.
Will you choose?
So this one's, we'll take a second to look at this. This is all related to it. So then how do we, send out these projectiles? The classic ways, you have a chemical explosion that happens and then a pressure wave and it shoves it out the barrel. The other way that they could do it is these electromagnetic rail guns. And these are real. They actually have them. They're also they're like in like Call of Duty and stuff like that. Can't you get like a rail gun, like a handheld rail gun? No? Yeah, I mean, it's science fiction, but we actually have them.
James T. Kirk as your fleet commander, a pioneer of space exploration.
Science fiction.
This is the US military's most powerful cannon, the electromagnetic railgun, which can shoot up to 100 nautical miles at Mach 7.5 and impacting the target at Mach 5, using only energy as its propellant. The high-velocity projectile will destroy land, sea and air targets purely from its kinetic energy, rather than with conventional explosive warheads. So what is a railgun? Well, the EM railgun launcher is a long-range weapon that fires projectiles using electricity instead of chemical propellants like gunpowder. Magnetic fields created by high electrical currents accelerate a sliding metal conductor or armature between two rails to launch projectiles at 4,500 miles per hour. Basically, it shoots a big solid metal projectile at very high speeds at vast distances and does damage using kinetic energy, only using electricity to shoot.
I think that's pretty interesting, right? 2,000 miles per hour versus 5,600 miles per hour, right? Pretty cool.
The railgun works by storing power for several seconds, generated from an external source, like a ship. After the weapon is charged with some 32 megajoules of energy, its capacitors send an electrical pulse down two long rails, one negatively charged and one positively charged, generating an electromagnetic field that fires the projectile along the two rails at up to Mach 7. Using extreme speed, the warhead impacts with high kinetic energy, ripping a hole through whatever it was aimed at. The 25-pound projectile is a non-explosive bullet, like a big dart, inside an aluminium alloy casing or sabot that falls away after the projectile leaves the barrel. The greatest advantage of an EM railgun on a naval vessel over traditional explosive round weapons is the safety aspect, as no propellant is required to fire the projectile, and no explosive rounds are stored in the ship's magazine. Railguns have been around a long time in sci-fi TV shows and movies.
Okay. I mean, pretty cool stuff, right? Right. I own lots of guns, right? I do. I mean, I grew up in Montana. But then, like, this argument of, like, oh, we need, like, assault rifles so that, like, we can they got shit like that, right? Like the military has got that, right? Like, they could just poke you out and then it's like, oh, let's shoot them with the railgun, right? And then... Right, like I understand numbers, and I get your argument. But then, then you just see those the weapons that the U.S. military has, and you're like, oh man, right? Like you see how they've taken out specific targets with drones. They shoot these non-explosive missiles that have knives on them, right? Have you seen like swords that pop out right at the last second, right? And then they don't explode, so you could just target one person as they go through this thing. It's like, yep. Okay, anyways. It's I don't want to tread into political stuff, but when I see that I'm just like, holy shit. Right? Right. Okay. So let's talk about this. We're in the middle of this. Right? We're talking about normal tangent coordinate system, right? We're talking about 2D and 3D motion. And sometimes we did Cartesian coordinates, but sometimes you want and we're going to see some examples, sometimes you want something else. That Cartesian coordinates is going to break down. It's not going to be as easy to use Cartesian coordinates, right? And so, so we're going to introduce the other one. This one's called normal tangent. It has to do with when you have a path. So this thing's traveling on a path like a car going around corners and stuff like that. That's harder to define, like the accelerations and stuff like that in Cartesian coordinates. Way easier to do in this normal tangent coordinate system, right? The normal tangent, you got one vector that's pointed in the tangent direction, right? Tangent to the path. It's always tangent to the path. So if the path changes, it changes too. So these coordinate systems are moving. And the other one, the normal one, is perpendicular to the tangent direction, but it's pointed towards the instantaneous center of curvature. So at first, it's curving to the left. At the first year you see, it's pointed to the left. And then at some point it comes over and it starts curving to the right. So then the normal tangent, or the normal switches sides and goes the other direction, right? So that's that coordinate system. These things are just like, you treat them just like I's, J's, and K's. When you write them down, you just say, oh, I got something in the ET direction and something in the EN direction. Like before we wrote I and J and K, now we write ET and EN, just to say which direction it's moving, okay? And then always keeping in mind that the direction that ET and EN are moving are constantly changing as well. ET and EN are always moving around. But we can still define velocity and acceleration in that coordinate system. It's just globally what's happening. It kind of gets lost a little bit. All right, so in terms of velocity, that velocity is always in the ET direction. So you'll notice that like when we talk about velocity, that's a vector, but it's only in the ET direction. There is no EN direction. There is no plus EN. There can't be because its velocity is in the direction of the tangent. If it's not, then you're not on the path and you're going somewhere else. So it's only in the ET direction. And then we took the derivative of that velocity and it gave us the acceleration rate, the time rate change of velocity. And we ended up with this, right? So this is the equation. We're going to simplify it here in a second. But just to look at it really quick, this is the change in speed along the path, right? It's how velocity changes along the path. It's in the ET direction. And then you have this component right here, v times omega, in the EN direction. And so this is the change in direction, right? So you have acceleration associated with change in speed and acceleration associated with change in direction. And what's nice about this coordinate system is they end up in two different terms, right? You have the ET direction, you have the EN direction. Cool. That's where we stand. We usually don't see it. You haven't seen it in the. You've talked about centripetal acceleration before, but usually don't see it in that form. Let's talk about other forms of theta dot. We can write this a couple different ways. Okay. I'm going to use this as a way of describing it. All right. So if this thing's traveling along a path, and this angle right here we'll call d theta. It's going from one angle to another angle. That angle is changing. Okay. It's coming around the instantaneous center of curvature. That distance there is then rho. We defined that before. The radius of the curvature we're going to call rho. And if I want to know the distance along this path in between here, right, we're going to call that ds, right? How is the position along the path changed given that d theta, okay? And so we treat this as just an arc length, okay? And so you can relate rho, d theta, and ds to each other. And basically it's this. Rho times d theta is equal to ds. ds is equal to rho times d theta. This is going to be a theme that comes up a lot in this class. If you want to figure out the distance along an arc, you take the angle in radians and you multiply it by the radius, right? And if you think about it, that's how we calculate the circumference of a circle, right? You take the circumference of a circle, the total distance around that arc is 2 pi, and then you multiply it by the radius, and so it's 2 pi r. That's how you get the circumference of a circle. It's just that angle multiplied by the radius. Yeah.
Is rho from the origin to the path?
Yeah, well, it's not for the origin. There's not really an origin. It's just the instantaneous center of curvature. Because technically this thing's going around like, it's kind of like a circle, right? And it changes, and so that rho is changing as you go around and stuff like that, but it's the instantaneous center of curvature. So if that was a circle, it's the radius of that circle, right, at that instant. Okay? Yes?
If you're traveling along a path and you have some curve in one direction and then it flips directions, I know that central component changes.
Yep.
But if you don't, and let's say you're going along a curve and then it just flattens out and it's straight, that path is straight, does it just stay that way until there's a new center of curvature?
Yeah, I
That
think
changes
so. Yeah,
direction.
it gets weird, but yeah, technically, I think it would. There would be no center of curvature as it was floating around. It'd be zero, and then once it started turning, it would jump over to the other side. Yeah. Yep. So then it would become zero. That's right. So then the other thing here to note too is this is in differential space, right? This is like a really minuscule, just like instantaneous. Like imagine that d theta being like super, super small. Like that's what we deal with is like when we do these derivations, we're talking about like at that instant in a differential space, really, d theta goes to zero, these things become true, right? So, okay. So here, ds is equal to rho times d theta. So now we can kind of put that in before, right? V, we're just trying to get a different form of these things, more usable form of that previous equation, right? So the velocity is ds dt, right? ds, we just said what s was, or what ds was. That's just going to be rho times d theta. Rho times d theta all over dt. Right? I just substituted in that. I just took this, right? Right? D theta dt is omega, right? Rho times theta dot, or sometimes we just call that equal to rho times omega. Right? And you can kind of rearrange this thing, right? That's kind of what this is doing right here. Right? I don't know why I put that in big white letters here, but there you go. That's just a different way of writing it. So you can write this as omega, we can write it as theta dot, it could be the velocity over rho, right? And we could take that and put that into our definitions down below. So that's just a different way. We'll talk about that in a second. It's just a different way. Omega can be written in these different ways. Okay. So then in summary, summarize what we just learned about velocity and acceleration in this coordinate system. Right. This is velocity. Right. Velocity is going to be v in the et direction or ds dt in the et direction. Right. ds dt is the change of speed along the path. Right. The acceleration this is how the book kind of describes it, is they say it's AT in the ET direction and AN in the EN direction. Right? They kind of break it down like that. They say AT is V dot. Right? How is the velocity changing along the path? Right, so that would get substituted in there. And then the AN component is the centripetal acceleration component, and there's two different ways to look at that. I don't know why I have that one already boxed there, but it's either one of these. Right? It's any of these really, but the ones that are more usable are what I have boxed in black there. Right? So it could be V times theta dot. You could write it that way. You could write it as V times omega. You could write it that way. Or more useful is V squared over rho, right? Because usually in these problems, you're either going to know what omega is or you're going to know what V is, right? And they're related to each other. V times R times omega will give us V, but they're related to each other. But sometimes you're going through it like, oh, I know my velocity, I don't want to turn it into omega, so you would use this. You would say that AN is V squared over rho, right? That's straight up, right? But you might know omega. Omega might be what you know. If you know omega, then you would use that AN is equal to rho times omega squared, right? It just depends on where you're at, what type of problem you're working on. Both of them give you the exact same answer. Right, it's just, are you going to terms of velocity along the path, or are you going to be talking about the change of angle along the path? Okay, so that's the summary. That's everything that we need to know about that. Okay, let's apply this to a special case, which is something traveling in a circle. Right now, we haven't said things are traveling in circles, just any path. Let's look at what it means when something travels along a circle. This could be simplified quite a bit. Any questions about that so far? Good. Okay, the instantaneous center curvature. Right, so something's traveling around this path right here. It's traveling around. Let's say it's got an omega like this. Right, it's a circle. It's traveling around with omega, so it's rotating around that direction. or it's traveling. That particle is traveling around that circle. Okay, in that omega direction. So in this coordinate system, I would have a direction here, and then I would have one pointed this direction. Oh, a straight line. Right? So this would be the ET direction, and this would be the N direction. Okay? And it's worth pointing that out. Like, you know, when I do these types of problems, I draw those coordinates on my particle, right? ET's in the direction of motion, tangent to the direction of motion, EN's pointing back to the instantaneous center of curvature. It's also worth noting, like a short time later, right, my particle's going to be over here, and when it's over here, then my ET is that way, or sorry, my EN is that way. And then my ET is this way. Right? That's worth pointing out. I mean, this is kind of demonstrating, like, look, this is, your coordinate system's constantly changing. Your solution is going to be like, you know, it's going to be a certain amount in the ET direction, a certain amount in the EN direction. You're like, well, which direction are those things pointed? I don't know. It doesn't matter, right? We just know that one's pointed back to the middle and one's going along that length right there. And we'll see as we do some examples. You're just like, you know, sometimes you do want to know exactly which direction it's pointed, and then that's where we can convert between normal tangent and Cartesian coordinates. Like if you really need to know the absolute position or the absolute velocity of something in space relative to something else, then you do have to get everything in terms of Cartesian. But just like for solving these, it's okay to be like, yeah, I know that, like if I've got a ball on a string and I'm whipping it around in a circle, I don't really care like exactly like where, and I was like, oh, what's the tension in the rope, right, as I'm whipping it around? Well, I don't really care exactly where the global position of that ball is when I'm calculating that T. I just care what the T is in that ball. And that's where something like this comes in. Like your forces in the EN direction would tell me what the T is in that rope as I was whipping it around. It doesn't really matter where it is in space. I think I've covered that off. Okay, so special case here. Our rho, in this case right here, our instantaneous center of curvature is going to be equal to the radius. Right, radius of the circle, that's given to us in this kind of problem statement. It's right there. So that rho is equal to R. Right, S then would be equal to R times theta. Right, if again this ties back to arc lengths, right? If I want the arc length S, I just take the radius and I multiply it by the angle, right? So S is equal to R times theta. So when I talk about velocity, that's equal to ds dt. I'm going to substitute in there dr theta dt. Right? R is constant for a circle, so that comes out, and so all you're left with is R times theta dot is equal to R times omega. Right? So if I want to calculate, if something's traveling around in a circle and I want to calculate its velocity and I'm given its omega, it's just going to be R times omega. That's the relationship there. This is going to, if we're talking vectors, this is going to be in the ET direction. Oh, look at that. I already wrote that down below. Okay, anyways. And then the AT direction, my acceleration in the tangential direction is equal to dv dt, change in speed. This would be d times r omega dt, right? We just determined that v was r times omega. R is constant again, that comes out, so this is going to be R times omega dot, which is equal to R times alpha. And that's going to be in the ET direction. Right, that's just the change in speed component, right? That isn't the change in direction component, that's just the change in speed direction. Right? Change in speed component. Right. Lastly, AN, our AN we kind of covered this last time, or just a minute ago. It's going to be v squared over r, or it's going to be r omega squared. Either one. Right? Depending if you have omegas or if you have velocities. So for a circle, that's what this thing simplifies down to. And that's what's just written down below. This is what I have above there. My velocity is just r times omega. And you could use either form of these for the accelerations. Okay. What's interesting, right? And this adds so much confusion, but that's why I'm gonna address it now, and we'll see it later. When we do polar coordinates, that's next, right? After we do a couple of examples, probably on Monday we'll do polar coordinates. Polar coordinates, when you look at it in a circle, it'll be these same equations. Okay, so that's where it adds confusion. It's like, well, if I have something traveling in a circle, do I do polar coordinates or do normal tangent coordinates? It doesn't matter. It gives you the same answer. They converge on each other. The one thing that's slightly different is in polar coordinates, this guy will actually be pointed that way. It'll be actually out. That'll be one of our directions is going to be out away from the center. And then one of these terms, this guy will be negative, and this guy will be negative. But we'll get to that. I just want to point that out, and because I know there's always confusion, like which one do I do? It doesn't matter. You could use either one. Okay. One last bookkeeping thing. This is what I said before, right? Like I don't know which direction these things are pointed. I don't really care. When you're solving these problems, I'm just after a certain point. Sometimes you might. Like if I was like another car over here, and I was like, oh, you're looking back at that car, where's it at, where's it going, stuff like that. Or if I was trying to hit something that was traveling in a circle, like I was trying to shoot a projectile at it or something like that, I do care where it's at in space at all times. And so you can convert between the normal tangent coordinate system and Cartesian coordinate system. Right? We'll do an example next week, I think, where we have to do this, but there's a way to do it. Okay, and so if something's traveling along this path, right, that line right there is a path. Okay, and let's draw our coordinates on here. Right, if it's traveling along the path right here at the origin where I've drawn my origin, it's going to have, this is going to be the ET direction. Right, and then perpendicular back towards the instantaneous center of curvature. That's the EN direction. Okay. I'm going to move this out of the way. I got a little over there. Okay. And so I can actually, and so what you do is just put a coordinate that's centered at the exact point that you're looking at, right? And then at this point, I mean, it is how much of the component is ET in the X direction, and how much of the component ET is in the Y direction, right? It's just geometry at this point, right? I break this up into a couple of different components, right? This ET is gonna have this guy, and it's gonna have this guy, right? And then this guy over here, EN, is gonna have this component and this component. Right? So I can convert those things. Right? And what you do, I mean, I'm not going to go through all of it, but that's where it comes from, is breaking it down like that. This is the angle theta. I should mention that. That's the angle theta. And what it looks like is this. ET hat is equal to cosine theta in the I direction plus sine theta in the J direction. Actually, that's really easy it's actually really easy to see, right? Cosine theta, ET has a magnitude of 1, right? So cosine theta in the I direction, right? And then plus sine theta in the J direction is where that thing can be broken down. You could do something similar for the EN direction. The EN direction, this is equal to negative sine theta in the I direction plus cosine theta in the J direction. Right? And so how you use that, right? Like I said, we'll do it a little bit later. But basically what you do is you do it in normal tangent coordinate systems first, and then after you do it in normal tangent coordinate system, every place that you see an ET, you write that. Right? So you replace your ET hat with cosine theta in the I plus sine theta in the J. And every place that you see in your solution that says En, you replace with negative sine theta in the I plus cosine theta in the J. That's it. Right? And that'll switch from normal tangent to Cartesian coordinate system. Usually you go that way. Okay. Anyway, back to wasting space on my notes. Page later, we'll do an example. All right, so there's a car traveling on a circular path. That path has a radius of 300 meters. Speed is increased uniformly from 15 to 27 meters per second in 3 seconds. And it says find the magnitude of acceleration at the velocity equal to 20 meters per second. Okay, this is a fairly straightforward and easy problem to do. Okay, it's after the acceleration, right? This is what it asks us for. So let's just write down this is something traveling in a circle. So let's write down what acceleration means in traveling in a circle. You say acceleration, it's a vector, right? Acceleration is equal to AT in the ET direction plus AN in the EN direction. Okay. AT is the time rate of change of speed along the path, right? So let's say AT is equal to dv dt, right? And they kind of give us some hints there, right? They tell us what that, they tell you it has an uniformly increased from 15 to 27 meters per second in 3 seconds. So here we know that it went 27 minus 15 over 3 seconds. So it's an average acceleration, right? So if I want that, this will be 27 minus 15, right? That's how much velocity has changed, right? Divided by 3 seconds, right? And so if you do that, you get this 4 meters per second squared. Right? That's just the AT component. And that's the average acceleration. Right? The AN component, AN, would be equal to either R omega squared or V squared over R. Right? I can use either one of those forms, right? In this particular case, the V squared over R is easier because they tell us they want the acceleration when the velocity is 20 meters per second. So they're giving us what the velocity is that they're looking for. So in this case, using the velocity one's a little bit easier, right? Because I'll just put in that. Could I use the other one? Yeah, sure. I just have to calculate what the omega was. I would take my velocity and divide it by R, and it would give me my omega, and then I put it back into there, and then you can go that direction for sure. But the fact that they just give us that velocity, I would just run with that one, the V squared over R. So this is going to be equal to 20 squared divided by the R, in this case, is 300. Right? This ends up being 1.33 meters per second squared. That's the AN component. Right? So my acceleration vector ends up being equal to 4 in the ET direction plus 1.33 in the EN direction. And the units are meters per second squared. Okay, so that is what my acceleration vector is. All right, we're not quite done. The problem statement says that it wants the magnitude of the acceleration, right? So how do I get the magnitude of acceleration? What does that mean? What's that? Huh? Yeah. It's square root of the sum of the squares, right? So I'm going to square 4, I'm going to square 1.33, and I'm going to take the square root of both of those, right? It's what the hypotenuse is, right? This is a kind of making up a triangle. We need to figure out what the hypotenuse is, what the magnitude is, right? And so that's the last step. And usually you sometimes see it written as this, right? This they put the bars on the outside. Sometimes that means absolute value. Sometimes it means magnitude. In this case, we're going to refer as magnitude. So this is going to be 4 squared plus 1.33 squared, and that ends up being 4.22 meters per second squared. And that's our grand finale. Okay, so that's that. This is what I'm saying right now. So like I'm able to figure out, right? They tell us that information. I'm able to tell you what the magnitude of the acceleration is, or even break it down to 4 in ET and 1.33 in the EN direction. I can tell you that, right? Like, I mean, I know that. Well, where's ET and EN, right? Like, I don't really care where it is on the circle, right? I don't care. I didn't need it, right? I'm just after what acceleration the passengers inside that car feel, right? And am I going around the corner up at the top? Am I going around the corner at the bottom? Am I over the side? Doesn't matter, right? I just know that I would be feeling that kind of acceleration as I went around. I may have mentioned this before. There's a former professor here, and he used to mess it up instead of saying like, let's beat that, beating a dead horse, right? If you just keep saying that over and over and over. He used to mess it up and say, we're gonna beat this horse to death. That's a completely different image that puts in your head. So I jokingly say that, like I know I'm beating the horse to death when I keep saying this over and over, but for reals, it is important to get, and I know that it's where students get hung up in the past. Hey, beating a horse to death, very gruesome. All right, well, I'm gonna skip this one. This one is like. This is similar. They give you the position, and then you work your way the other direction. We did that before. So if I give it, theta is actually a position, and then if I want theta dot the omega, I'll take the derivative of that. If I want theta double dot alpha, then I take the derivative of that one. You kind of go that direction and then piece things together. It's not as interesting, but that's what that one's about. I can post the solution to that one later. All right, so this one's a little more interesting. I don't know, an electric car starts at point A. Why it's electric, I don't know. Just make it exciting and hip, right? An electric car starting at point A and accelerates to the right at AT is equal to 1 plus 0.2 t meters per second squared. So this thing's accelerating along that path at the value given right here, okay? And it says find the acceleration at point B, the velocity and acceleration at point B. So it's going to go whipping down this thing. It's going to accelerate all the way around that corner. Its acceleration around that corner is defined by that equation right there, right? And then when I get around that corner, not only am I going to have the tangential acceleration, I'm also going to have a velocity at B. If I have a velocity at B, that means I'm going to be accelerating, right? I have to be accelerating back to the middle. If I'm not accelerating back to the middle, then I'm not going around that corner, right? This is just a little foreshadowing, right? Am I accelerating? If I'm accelerating back that direction, there has to be a force to make me accelerate that direction. So that's why when you go around a corner, you're like stuck up against, the passenger or the door or something like that. You're leaning against that because that car has got to be pushing you back that direction. It has to be a force there to make you accelerate that direction. And that's what we're moving to is like, what is that force going to be? That's the next step. That's kinetics. This is kinematics right now. This is all still just geometry. I haven't talked about a single force yet. All right. So the first thing it wants is velocity. All right, so let's start writing down what the velocity is. Velocity vector, that is the vector. It is always in the ET direction. It's going to be V in the ET direction, always, which is equal to ds dt in the ET direction, right? The acceleration. Sometimes I like to do this. It's like, where do I start? I just kind of write down the equations for these things. AT in the ET direction plus AN in the EN direction is equal to V dot in the ET direction plus V squared over R in the EN direction. I'm going to choose that form for it. Okay, just kind of laying things out. Right? This is, remember we said when we do like these 2 or 3D problems, it's just a bunch of 1D problems. So we're gonna have these 1D problems as we go along, and it's gonna help us solve this, right? And so one of the first things we need to do is they give us the acceleration equation. It's the acceleration of function of time. So we have to start with acceleration of function of time, then go to velocity, and then go to position, right? And so let's start the acceleration component here. Then we'll make it through this, and that'll probably be it. So they give us AT. It is a function of time, is how they give that to us, which is 1 plus 0.2 t. That's equal to dv dt. Right? I put all the t's together. Right? So this is going to be 1 plus 0.2 t dt is equal to dv. Integrate this thing. That thing is going to be integral from 0 to t, and this is going to be an integral from v naught. Well, we're going to start out at 0, right? Starting at 0 position to v. Okay. If I carry this integral out, this is going to be t plus 0.1 t squared. Right, that's just the integral on the left-hand side, and that's going to be equal to v. Okay, and this is my velocity as a function of time, right there. It kind of pops out of there. Uh-oh. All right, it's back. Okay, so just carry out that integral. Now I have velocity as a function of time. Right? I want to point out I did that integral this morning in my head. Just want to point that out. I didn't use my calculator for it. Thank you. Thank you very much. It's a simple one. Okay. Let's keep going here a little bit. Now I want to get to position. Right? So this whole thing is equal to ds dt. Right. And if you don't remember how to do this, you go back to our 1D problems and kind of laid out how to solve these problems. Right? And so this is going to be t plus 0.1 t squared dt is equal to ds. This integral is going to go from 0 to t, and this is going to go from 0 to sf. We haven't figured that out yet, but that's going to be wherever the final position is when it goes around that corner. I mean, we're going to be able to get it, right? Because I know, right, the final position is right here, right? So I know that this thing's going from here to here and then around that corner, and I can calculate that total distance. So I do know what SF is. I just don't know yet what it is. All right, that's right. Finish this thought up here. All right, let's carry out this integral, and then we'll call it good here. So this one is going to be t squared over 2 plus 0.1 t cubed over 3 is equal to, right, SF. Okay, and once I like I said, I know what that SF is. We're out of time, but we'll pick up from this next time. SF, we know that distance. When we solve that, then we can figure out that T. Once we get that T, we can then kind of work our way around. Okay, and actually, once we get that T, we're almost there. But this is what I'm saying. It's just when we said this before, it's just a bunch of 1D problems put together. And here's that 1D problem and how you solve it and stuff. And we'll keep going from there on Monday. Cool. Have a good weekend. Maybe get a slinky and take it to a party tonight, right? You know, just saying, show it off. Say, yeah. Yep. It's gonna be the whatever that 200 plus the radius multiplied by pi over 4, or whatever it is, whatever that angle is. Yep. Whatever 90 is in metric. Yeah. Pi over 2.